Hello everyone. In this lesson we are going to learn about another extension of Euler's method and which is the Heun's method. The Heun's method is actually an improvement from the Euler's method. So let's dive into the details of Heun's method. Okay, a fundamental problem in Euler's method was that the derivative at the beginning of the interval was assumed to apply across the whole interval. Okay, so that's the difference, that it is not necessary that the derivative is remaining constant across the whole step size h. The derivative can change actually, and it actually does, and that's the main source of error in Euler's method. So in Heun's method we are actually going to estimate the result and estimate the slope with two different equations. That means we are going to extend the idea of Euler's method for a better approximation of the slope within the whole interval. Okay, so we are going to use two different results. One is from the initial data point, that means the derivative result from the initial data point, and another is the derivative result from the end data point. So within an interval we will have two boundary points, the initial and the end data points. So we are going to approximate the derivative at these two boundary points, and then we are going to take the average of those two data points, two derivatives actually, and that average value is going to represent the average slope within that interval. So that's the basic idea of Heun's method. We are not just keeping the derivative value across the whole interval to be constant, rather we are just taking the average of the first and the last data point of the interval. So that's the basic idea of Heun's method. So in Euler's method, if you remember, the slope at the beginning of the interval can be calculated something like this: yi prime. So this is the slope at the beginning of any interval, and these can be used. This slope at the beginning can be extrapolated linearly to get the value at the next data point. That means xi plus 1, which is yi plus 1. Okay, so this is the equation that we have used in Euler's method to get the approximated result of the function at any data point based on the values of the previous data points. Okay, but in Heun's method we are going to approach further. So this is in Heun's method, this is not the final equation, this is an intermediate equation, and it is called the predictor equation. Okay, this is the predictor equation which predicts the slope of the function at which actually predicts the value of the function at the next data point. That means at the next boundary, at the end of the boundary. Okay, so this is the predictor equation, and that's why we are just using a new notation here, yi plus 1 with a superscript of 0. Okay, so it provides an estimate of yi plus 1. It's not the differential value, it's just an intermediate equation. This is not the final result. So we are going to estimate a new slope at the end of the interval by using the predicted result. This is the predicted result, yi plus 1 0. So we are just going to substitute this value inside our ordinary differential equation, and we are going to get a new slope at the end of the boundary, at the end of the interval. So once we have the two different slopes at the initial point, at the end of the and also at the end of the point, we will just take the average of these two data points, and this is going to represent the average slope within the whole interval. So that's the average slope within a single interval. In Euler's method we were using a single slope that was actually the slope at the initial data point, but in case of Heun's method we are just using two different slopes at the initial point and at the end point. So if you just substitute the two values here, we will get an average slope something like this, and now this average slope is going to be replaced into the original Euler's method to get the yi plus 1. That means the final predicted result, which looks something like this. Okay, so in Euler's method we had a single term here which was f of xi comma yi, but in Heun's method we are just taking the average of these two slopes, which is at the initial data point and the end of the data point. So this is the final Heun's method equation, and this is also called the corrector equation. The previous intermediate equation, the intermediate result that we are calling, which was the predictor equation, but now this is the corrector equation. Okay, so the Heun's method can be easily represented at a summary using the predictor equation and the corrector equation. So this is the overall Heun's method. Now once we get the final result, that means the yi plus 1, the value of the function at the next data point, using the corrector equation, we can again substitute this y plus I plus 1 into the corrector equation again. As a result, we will get another superior result actually. That means this yi plus 1 will actually correct the average value a little bit more. That means we will have a more representative average slope within an interval actually. So we can easily continue to substitute this yi plus 1, the corrected value, in the corrector equation again, and then we will get a new corrected value and substitute the value in the corrector equation again, and so on. So we can just go on to fine tune the corrected result at the end of the boundary. So how we are going to stop this iterative form? What is the criteria to stop the iteration? So within the two iterations, the previous iteration and the next iteration, we will have two different corrected results which are denoted something with the index j. That means the j is the index that corresponds to the iteration on the first iteration, the second iteration, third iteration, and so on. So at the two subsequent iterations, we will calculate the difference, the approximated percentage difference between the results, that means the corrected results, and we are going to call it the approximated difference, and that approximated difference is going to be limited by a predefined error limit. So we have to define an error limit, and once that approximated result reduces below the predefined value, we will stop the iteration. So that's the criteria that we have been following in the whole course, right? So that's how we can stop the iterations. Now let's look at an example here. We are given a simple differential equation. This is a first order differential equation, which is y prime equal to 4 e to the power 0.8 times x minus 0.5 times y. So this is the main equation, ordinary differential equation, and we have the data ranges from x equal to 0 to x equal to 4, and we have the step sizes to be 1. Okay, and we are also given the initial conditions, which is x equal to 0. The value of the y is 2, and we are going to use the Heun's method. Okay, now in the step 1, we are going to find out the value of the function at the first data point. The first initial data point was x equal to 0, and the step size is 1, so the first data point is going to be at x equal to 1. Okay, so at step 1, we are going to calculate y1, and y1 is situated at x equal to 1. Okay, so in the step 1, in the first iteration, we are going to calculate the approximated result using Heun's formulas. So at the initial point, that means at x equal to 0, we have a slope which is 3, and using that slope, we are going to use the predictor equation to get a value of 5. So until now, this 5 was the result when we were using the Euler's method, but right now we are not using the Euler's method, we are using the Heun's method, and that's why this 5 is not our final result. If this was the Euler's method, this was the final result, but now we are going to use the Heun's corrector equation. So this 5 is going to be replaced into the corrector equation. So we are just going to use the intermediate equation to get an approximated slope at the end of the boundary. So at the end of the boundary, we are going to find out a new slope, which is f of x1 comma y10. This y10 was achieved from the predictor equation. So this is the slope at the end of the boundary, that means at x equal to 1. So we have two different slopes at the initial point we have initial slope, and at the end of the boundary we have a new slope. And now according to the Heun's method we are going to take the average. Okay, we are going to take the average of these two slopes, and the average turns out to be 4.701082. This is the average slope within the whole interval. That means the interval is situated from x equal to 0 to x equal to 1. So that's the average slope within that interval. Okay, now we are going to use the character equation. Inside the character equation we are going to replace the slope with this average value, that means 4.7082. okay, and now we got the final result, that means the corrected result to be 6.701082. So this is the first corrected result. That means at iteration 1 of the Heun's method we just got the corrected result to be this. And now we can again substitute this result into the character equation again. Okay, and that means in the next iteration, at iteration 2, if we just substitute this result, we will get another corrected result. This is a fine-tuned result, a finer result. Okay, so that is 6.275811. So this is the result at iteration 2. And now again at iteration 3 we are going to substitute the result into the third iteration and get a new result which is 6.382129, and so on. So that means we can go on by substituting the corrected result into the character equation again and again, and we will get a finer result. Okay, so once the results of the two successive iterations gets close to each other, and we will stop the iterations. So in these predicted results, and so at one point the result at x equal to 1, as I have said, these results will converge actually to a certain point. So that will be our final result at x equal to 1. So once we get the result at x equal to 1, we will use the result at x equal to 1. That means we will use the value of y1, final value of y1, to get the value of at the next data point, which is at x equal to 2. Okay, so we are not showing you the details calculation at the next iterations and then the next steps. We are just showing you the final results within this chart. You see there are two different columns. These are the results whenever we are using a single iteration in the Heun's character equation. And on the right hand side we have the results whenever we are using 15 different iterations within a single step. Okay, so as a result the difference is very straightforward. Look at this. Whenever we are using a single iteration, the errors are much larger than the errors whenever we are using the 15 different iterations. Okay, so using different iterations we are just reducing the error. Okay, so in Heun's method there is a provision that we can use iterative results to get a more precise accuracy, to more precise result actually. Okay, so these are the results of Euler's method, and this is the true solution. And with the same step size, if we use the Heun's method, look at this, the Heun's method is much closer to the true solution with the same step size. Okay, that means Heun's method is providing you a better result from the Euler's method. So Heun's method is not actually a new method. It actually extends the idea of the Euler's method. It changes the definition of the slope within a boundary, within an interval, and that's the difference between Heun's and Euler's method. So for this simple extension from the Euler's method, Heun's method is actually providing a much precise result than the Euler's method. Okay, so in this lesson we have learned Heun's method. We have seen that the Heun's method consists of two different equations, the predictor equation and the character equation, and the character equation can be used iteratively for a better and finer results. Okay, so please try out the MATLAB code that I have attached with this method, with this video for Heun's method. Go to the details of the code. In the next lesson we are going to learn about another improvement of the Euler's method, which is called the midpoint method. We have just seen an extension which is the Heun's method, and we will see another extension which is called the midpoint method in the next lesson. So till then, thank you so much.